Last week we talked about the gradient descent optimization methods for training neural networks. And we went through the backpropagation algorithm, the error backpropagation algorithm, which involved taking the derivatives of different elements through the network and working our way from the output of the network down through layers, distributing the gradient to the different parameters as we made our way down. In that case, we were computing the derivatives ourselves, and we had sort of generic formulas that we used to go down a layer. Today we're going to work on, look at a way to automate that process more generically. So this lecture is called Auto Differentiation. The goal here is to learn a way to automate the computation of gradients and derivatives. So consider this expression, f equals sine of x plus x times y. Now if I want to compute that, I would do something like this. I would say x, I'll just start with this and it'll make more sense later. X is a variable and y is a variable, so I just sort of declare those variables. Then I could say a equals sine of x. I could say b equals x times y. And then I can say f equals a plus b. Now I'd like to draw the computational graph of that, starting from f, the output, and making my way down. So let me just reiterate that that is a, and then this is b. We'll use these in our graph. So I'm going to start at the top with f, and I'm going to draw it like this, in a circle with a little line underneath it. Let me make the f a little bit clearer there. Now the f comes from adding a and b. So it's coming from this operation of adding. And what is it adding? A and b. So these two little things point to a and b. So I'll put a here, and I'll put b over here. And so that line means depends on. Okay. I guess I could do that as well. So now the a comes from taking the sine of x. So this comes from the sine function. And the sine function also depends on x. The b part comes from adding x and y. So it comes from this addition operation, which has two arguments, one of which is x, and the other of which is y. So this is the full computational graph of that expression, or we might call it an expression graph. Because it's the graph that represents an expression, mathematical expression. Now this little arrow here, where a is pointing down to the thing that created it, I'm going to refer to that as a creator pointer, or creator reference. So a was created from the sine function. We'll use that later on. Okay, notice that we'd actually build the data structure in the order that's opposite to the way I drew it. So we'd actually start with x and y, and then we would, for example, with the x thing, we would then do the sine and then create a from that. The sine function would create a new output called a, and so on. So we'd make our way from the bottom to the top. Whoops, draw red. Okay. Right. So these expression graphs have two different objects, and I've drawn them differently with squares and circles. They're variables and operations. So, and I'm kind of showing the two different objects here. So variables will be objects, and by objects I mean we're going to create classes, like programming classes for each object, for each type of thing. Variable, here I'm calling it X. Now variable has a couple different member variables inside it. It has a value, and it also has a creator, which points to, or it's a reference to, an operator. So operator is x.creator. Okay, so x.creator evaluates to an operator object, or reference to an operator object. Sorry, operation. I'm trying to use the word operation instead of operator. Okay, the operator class, I'm showing just an example here of the plus operation. It has arguments, and I'll call them A and B here, and they are references to variable objects. So variables have references to operations, and operations have references to variables. In this case, the plus operation has two arguments. You could imagine an implementation that has two or more. I just did it with two. And there are other operations that have only one argument, like log or exponential, and there, you could have more than two. I'm just showing it with two. Okay, let's do another example. F equals A times B. So we're given objects A and B. If we're computing F equals A times B, then A and B must exist already. So what we do then is create, given A and B, we create the operation object. I'll do that over here. So it's times. Now, inside the operation object, we want to save references to the arguments. In this case, the arguments are A and B. Next thing we need to do is create a variable for the output of this operation. In this case, we'll create it and call it F. Okay, the last thing we need to do is make sure that F variable refers back to the operation that created it. So that's what this arrow is here. So set F dot creator to this operation. And so that's how we build up the expression graph. Now, if we want to evaluate the expression graph, we can. So we can use the expression graph to do the evaluation. Each type of object has an evaluate function. Evaluate function. So for the variables, the evaluate function has to make a decision. Either it returns its own value, or if it was created by something else, it basically passes the buck down to the thing that created it. So for example, in this expression here, I could, if I created the expression, let's say I created the expression graph and it gave me the output F. But let's say maybe I changed the value of A. I said A.val equals something new. Now I want to reevaluate the expression. I can start at the top at F and say, please evaluate. So it has to keep sort of passing down through the graph, asking each thing below it what its value is. And it keeps passing down until it gets to a variable that doesn't have a creator. It was just there to begin with. You could say it was created by the user. It wasn't created by an operation. So in the evaluate method, if the variable has a creator, we call it. If not, we just return the value. So I'll write it this way. If creator equals, no, is. This isn't really Python code, this is pseudocode. So if creator is none, we return the value. Otherwise, we return the creator.evaluate. So in other words, if it was created by the sign function, for example, instead of just returning the value, we say, oh, let's return the value of the sign function reevaluated. Okay, let me move this over a little bit because. Right, now for the operations, oops, I didn't mean to do that. Now, for the operation, its evaluate function, it's going to apply its own function to the arguments, but the values of the arguments might have changed, so we need to reevaluate those. So call evaluate on all the arguments. And once we've done that, compute and return the value. So by value, I mean the actual value of the operation applied to those arguments, not val. The val is something that's inside the var, the variable object. Okay, so I hope that's clear. Using that strategy, you can work your way down through the tree. Well, here's an example of it. Back to our same formula. Instead of writing it all out, I've just pre-written it. So if we want to evaluate f equals sine of x plus xy, and let's say we've already created the expression graph, and then we went and changed the value of y, for example. So we need to reevaluate everything. First, we call evaluate on f. Well, f was created by adding a and b, so it calls the evaluate function for a and b. Once those return and it has those values, then it'll finally add them, and you get your value of the expression. Okay, so for a evaluate, that's a variable. A actually, so it calls a evaluate, which is down here. Since a came from an operation, the sign operation, we call a creator.evaluate. So evaluate the sign function. So this is evaluating the sign function. It has to call evaluate on its arguments, which is x. So it calls x evaluate. Finally, we've reached a variable that didn't come from anywhere. It's just sitting there. It's what you'd call a leaf of the graph. So it returns a value, and we work our way back up through the call stack. And I could go through the same thing with b evaluate. It was created. B was created by a product. So it calls the evaluate on that product. Anyway, I'll stop there, but you get the idea how it works your way. It's basically a tree traversal, although it's not necessarily a tree. It's a graph traversal. Not a tree because we're calling x here, the value of x here, and the value of x here, but it's not relevant that it's not a tree. It doesn't matter. Okay, so we know how to build these expression graphs, and we know how to evaluate the expression graph. Now it's time for a joke. Here's my joke. Two cannibals are eating a clown. One cannibal turns to the other and says, "Does this taste funny to you?" Okay, now let's use the expression graph to take the derivative. How do we use that graph for computing the derivative? Each var variable stores the derivative of the expression with respect to itself. So it's the entire expression. So up here, the expression is sine of x plus xy. So you can imagine computing the derivative, I guess it would be partial derivative of sine of x plus xy with respect to x. Or you could imagine taking the partial derivative of that expression with respect to y. Okay, so, but as we went through, here, where's that? Here's the graph again up here. As we went through the graph, we created a number of different variables. We created f, which was the full expression. We also created a and b as sort of intermediate variables. So we will also compute this partial derivative of f with respect to a and the partial derivative of f with respect to b. And this will all be part of the process as we go to get all the partial derivatives with respect to everything in the graph. Okay. So let's start with kind of a theoretical example. I've got f, little f, equals big F of big G of big H of X. So it's kind of this sort of like peeling an onion, a bunch of layers of functions. So what I will be computing, for example, or x dot grad will eventually store die f by die x. So that is the x dot grad will store, stores it in a member called grad. Okay. So it's the partial derivative of the full expression with respect to that variable. Okay. Now, to make our lives a bit easier, I'm going to say, I'm going to call little h the value of big H of x. And little g is going to be big G of H, little h. Okay, so now I basically, those are the labels I'm going to use for these intermediate variables. Okay, so if I were to compute this using sort of, first year calculus, I would say, okay, the partial derivative of my little f with respect to x, well, I have to start peeling the onion, right? It's die big F by die G. G is the input. Little g is the input to the big F function. And then die G of H of X by die X. Let's unwrap the second one now. Peel off the G thing. Die F, I'll do it this way now, die F of little g by die G times die big G of little h by die H times die big H of X by die X. That's the full chain rule now. So f of little g is what I'm calling little f, so I can rewrite it like this. Little g of h is what I'm calling little g. Little h is big H of x. Okay, so this I'm just kind of laying the groundwork for how we're going to use chain rule in this expression graph. Looking at this figure on the right here now, we have our output f, and we're going to start out with die f by die. So as f dot grad will be the gradient of the expression with respect to the variable itself. Not very exciting. What's the derivative of big F? Sorry, what's the derivative of little f with respect to little f? It's just 1. Okay, so that's how we get the process started. It'll always be that. The top will always just be 1. Now we'll work our way down through this graph. And as we pass through each function, that function will contribute its term to the chain rule. Okay, so to get down now to g, this variable down here, we have to pass through this big F function. And as we pass through it, presumably we know what f is, or f, the big F function knows its own derivative. So it knows how to compute the derivative of the output with respect to the input, which is what this is. It's just f prime of g. I mean, we don't, if we were actually writing it and we know what f is, then we would actually write an expression there. And we'll do an example like that later. Okay, now we can say g dot grad is di little f by di g. Which is this thing here. Okay, so we would have computed that. That would actually have a value, right? It would be whatever this evaluates to. The derivative of that function evaluated at g. Okay, now we can go down through g, big G function, to get down to little h. So di g by di h is g primed evaluated at h. That would actually be, after we've got values in this graph, g primed at h will actually be a numerical value. So once we've done that, h dot grad will be, now h dot grad is, what we're looking for is di f by di h. Okay, that's what h dot grad represents, right? It's the gradient of the full expression with respect to that variable. But that is built by multiplying down through the graph. So we have our df by df to start out, then we multiply by df by dg. Which way do I do it? Di f by di g. So that was passed down from above, times the part that this last layer added, di g by di h. Okay, so now we have we have h grad, the gradient of the expression with respect to h. Let's go down one more layer. We have to pass through the h function to get all the way down to x. Di h by di x is h primed evaluated at x, whatever that happens to be. Now x dot grad, remember, that's supposed to be di f by di x, but it's constructed by passing down through the graph by, it inherits this thing here. It inherits the gradient from above. So we'll get di f by di g by di h, and then we add on this last step, di h by di x. So as we work our way down through the network, where basically each function adds on, or each operation adds on its term in the chain, in the product that builds up the chain rule, and then passes the result down to the stuff below it. So it can continue, the stuff below it can build on that chain rule even more. Okay, so we start with a value of 1 at the top, and we work our way down through the graph and increment grad of each variable as we go, of each var as we go. By increment, I don't necessarily mean add. There will be times when we add, but in chain rule, it's actually multiplying. So each operation contributes its factor according to chain rule and passes the updated derivative down the graph to the things that it depends on. Okay, so let's revisit this example here. Let's compute the gradients of this expression. So we've got f at the top, and I guess I can say df by df equals 1. So the things in red are going to be the accumulated gradients with respect to the variables. And the things that are right in blue are just the sort of the derivatives of the functions with respect to their arguments. Okay, so the first thing we encounter, f comes from this addition operation. So I can, it's a plus b. So I can, on this side, I'm going to have di a plus b by di a, which equals just 1, right? If I take the derivative of a plus b with respect to a, I just get 1. And on this side, I get di a plus b by di b. That's also equal to 1. So it's not a very exciting or maybe even very informative first step, but that this one times this one is what gives us di f by di a, which equals 1 at this point. Now doing the same thing but on the other side, we get di f by di b equals 1, which again comes from multiplying this by this. Okay. Now, that's great, but those derivatives get passed down through the network some more. So for this a side, going through the sine function, it'll be computing di sine x by di x, which equals cosine of x. So that's the cosine of x is an additional factor that's going to be multiplied, will be multiplied on the chain of products, the chain of terms as it passes down. So that down here x, di f by di x will add on this sort of chain of products. So this 1 here times the cosine of x from the thing above it. So it'll be cosine, I'll just write like this, 1 times cosine of x. Okay, switching to the other side. On this side now, we have a product. So going this way, oh boy, that was erase. Going this way, we get di xy by di x equals y. And going this way, we get di xy by di y equals x. So for each of those two different branches, we'll send different stuff down. So this first branch down here, we have this 1 times this y. So we add on 1 times y. So after all is said and done, according to this, the partial derivative of that expression with respect to x is cosine of x plus y. Now for the di f by di y, it's basically 1 times x. It's this inherited derivative times the contribution from the operation above it, which is just 1 times x. So that equals x. And if you want to drudge up your calculus from first year, if you were to take the partials of that with respect to x and y, you would in fact get those expressions. But here we built it from the expression graph. So to facilitate this derivative process, this auto differentiation process, we add a function or add a method to each of the variable and operation classes called backward. Each object has a backward method that processes the derivative and passes it down the graph. So for variables, so imagine that this is inside the variable class now. When I've got this, I have to define this backward method. It takes s as input. So this s that it's taking as input, that's the sort of the accumulated derivative from everything above in the graph. So that's, if you like, that's the derivative that's passed down from above. So for example, for this a, it inherited a 1. Well, it was actually 1 times a 1. So it inherited that 1, and then it set its own derivative to 1. Okay, so this s is the thing that's passed down, the derivative of the stuff above it. Now this s, this will make more sense later, because so far we're just dealing with scalar functions. Soon we'll be dealing with multivariable functions, and so I'll say this now to help us later. The self.val, so inside this variable, the val member, the self.grad member, which we're about to increment, its gradient, and this s that's input, all have to be the same shape. So once we get to passing vectors and matrices around and gradient vectors, it's helpful to know that s has to match the size of the variable's val function or val member and the grad. So we say self.grad plus equals s. So we're basically incrementing this variable's gradient or derivative with the derivative of the stuff above it, and then we have to pass it down. So then we say self.creator.backward and pass s down. Okay, now for the operation inside the operation class, it's a similar story, but we have to actually compute the derivative of the operation and add that to the chain rule. Okay. So in this case, this s, and again, this is to help us later, the s that's input to the operation has to match the shape of this operation's output. S must match the shape of the operation's output. Okay, what do we do now for, we've inherited this, this derivative from above, the operation. Now what we need to do is, so I'm looking at this one here. What we need to do is for each of its arguments, compute the derivative of this operation with respect to that argument, multiply that on and pass it down to the backward function of that argument. Okay, so for x in args, in its own arguments, I could say self.args, we call x dot backward. Now, inside is the derivative that we're passing down to that variable. So it will be the s that we inherited from above, and we're going to contribute the I'll just write this, diop by dix. Okay, so that's adding the term on. So that's the derivative of the operation with respect to x. Operation with respect to x, that argument. So this is a bare bones implementation of auto differentiation. We're actually going to play with implementations of this, and you'll see that it makes your life, once you get it set up, once you kind of do the bit of pain to get it set up, it makes your life infinitely easier.